First thing, we'll have lab from week after, from February 8th. We're still waiting on a couple of chemicals, so that means the lab will start from Thursday, from next the Wednesday after, which is February 8th. Yeah. Yes. So this is again email address of GTA. Homework 1 will be from chapter 1, and this question, how semiconductors are different from conductors or insulators. What are some similarities? So you need to upload these answers on Blackboard in one PDF file. So if you submit 5 files, the system doesn't just downloads me one file, so upload one PDF file. If you have problem or you want to know how to create a PDF file, ask GT. It will help you to do that. So these questions come from the book. One is from a simple question in your understanding. So this is a paper that I want you to read before we get into oxidation. So this is something we expect to get into next week. All right, so we're going to talk about Cleanroom. What are some basics on the Cleanroom? How do we do entry, exit? What are points to remember? Of course, you have gone through these in the training, but there is always somebody who has some concerns, questions, or wanted to bring it up. So there is certain dress code that you have to follow. There is order of things that you do. Walking on mats, on the sticky mat especially. How do we do the gowning? So the process is called gowning, where you have to dress up in a certain order, put on shoe covers, and so on. And then there's air shower that we have to take. We have to stand there and rotate, so all the particles from even the coverall, they are blown away, and then we enter from that door and we exit from the other door. And there's how do we exit? That also requires certain process. Leave, but before we leave, we swipe the card, so there's the count is accurate on how many people are there. So, of course, no food or drink, nowhere up past that first door. After that sticky pad, you don't carry anything inside. Of course, cosmetics contain chemicals. We know now what nail polish, we have seen examples of nail polish. So cosmetics, it don't have the makeup because those chemicals may react with fumes or vapors of chemicals that we use. And if you have bags, books, can put them in lockers. They are placed beyond that door. If you are facing towards the cleanroom and elevator is on your back, there is a double door on your left. Past that door, there are lockers on the right side. Place your stuff in those lockers. You can lock them and leave everything outside before you go inside. Right, so take your time. So if you have any questions, always email us. We can get you the same page on the gowning and cleaning process, or on the preparation. How do we go inside and how do we get out of that? Right? Why do we do all that? So to keep to maintain the integrity of the clean room. First, the question is, what do we mean by clean? So clean is, we don't want any of the particles from outside to go inside. So we want to restrict the size of particles that are there in the air, because they will contaminate not just the process, the devices, the wafers. And there are limitations on all the things that we can or cannot do. There are three basic types of contamination. Physical particles which may land on a surface, films, or trace elements. So some are visible, some are not. So we can see particles. How do we see particles?
Look at them.
Which microscope? Just hold the wafers and look at it. But what is the smaller size? Smaller size probably that we can see with bare eyes.
10 microns maybe?
10 microns? Yeah, that's about the 5 to 10 micron is what we can see as a. If it's a line, we can see 5 micron easily. But if it's a speck, if it's a particle, which is probably you won't be able to see that. So what do? What can be first step of looking at the wafer?
Optical microscope?
Optical microscope. Just put it in and scan the area at low magnification. Right? So that can show you many things. Layers of foreign materials, the films, those are the chemicals that might leave some traces behind. Where can oil come from?
Our hands.
Hands, right? So we always have secretions. Of course, we never have bare hands inside the clean room, right? But if a glove tears apart, we have to change our glove. If we don't step out the clean room to get a new glove, we can put on new gloves while you're inside. But there's always chance that we can sneeze, we can cough, so things come out. So there are certain things that we do to get rid of chemicals. If we do some solvent clean, then there is a series of solvents that we use. So one would take care of or clean, remove the previous solvent, and ultimately we do a deionized water wash. So we'll look at what is deionized water, why do you want to use this. Trace elements, of course, if you leave some metallic ions, when you're talking about ions, it might not be a film, maybe some metal will be there on the surface, you won't see it. Once you do a high temperature process, what happens to metals? What happens to everything that we heat above melting temperature?
Melts or something.
Melts, right? Turns into vapors. And something that is free to go, free to roam around in gaseous state, what it can go in, you can see within the hard material. It's not easy, but it happens. So we'll see what is that phenomena when something moves against the gradient of concentration. So, of course, if there are metals, we cannot heat the substrate chip wafer up to high temperature because that's going to melt it. So melting is very important topic. So if a metal melts in a high temperature process, it's not just going to degrade the substrate, the electrical properties of the material. It's going to contaminate the container also. It's going to contaminate the chamber of the process. So if I have a machine, say oxidation furnace, right? So it's a tube, quartz tube. If I use a wafer and I had metal on there and I heat it up to 1000 degrees centigrade, the whole furnace tube will get these ions incorporated. So now if the next person puts his silicon wafer and does oxidation, those wafer are going to get these ions incorporated, metallic ion. So do we want semiconductor material to have metallic ions? No, that's going to change the whole electrical property. So we call it contamination. So it's, for a layman, it's not a big deal, but for devices, it's contamination. It's a huge issue. Right? There are in some other cases, there are other types of contaminations which we are not concerned. Right? In space application, what can be other types of contamination?
Which kind of applications?
Space application. When you send a whole rocket up in the space, it has electronics, right? It has devices and semiconductor-based materials. What are the issues there? Radiations, right? They can be UV radiation, other type of radiations which can change the electrical properties of those devices. So,
Is that really contamination, or is that?
it's a major area of research. How do we control radiation contamination?
Yes.
This contamination, right? So what are sources of contamination? The equipment itself, because in any given equipment we have number of gases coming in, reactions happening, products coming out of that reaction, and we have to remove those products. Some of those reactions may be highly corrosive. They might react with the material of the chamber, with the material of the encapsulating container of the equipment itself, right? So most of those chambers are inert for what reactions we do in there, but there is always some sort of etching or deposition happening. So it may not just remove the surface material, it may deposit something there, which may become an issue when the next person uses that equipment. Those deposited materials might degrade the next process. Liquids and gaseous chemicals. So they are gases flowing through, they are liquids going through, they can carry those contaminants. People are major source of contamination because we are always inhaling, exhaling. We have particles, skin coming out of things coming out from our skins, which can be major issue for devices. Devices are small, they're smaller than micron. Chemical and wafer containers, so the containers that we use to move the wafer around. In your case, it would be your tweezers, because you'll be holding your wafer with tweezers. So if your tweezers is not good, it's not clean, it's gonna screw up your wafer. Now think about it. Have to be very careful. Have to be, I would say, use common sense. So if I'm using this tweezer to hold my wafer and I put the wafer in a holder, right? Now what do I do with tweezer? Can I hold it in my ear? Can I put it on the bare surface table? Can I put it in my pocket?
If you had a pocket tissue.
Can I? Can I put it in a tissue paper? Roll it in a tissue paper?
Just
Tell me, can I put it on my ear? Why not? I'm contacting with lots of oil and skin flakes.
no, you don't know what's on the tweezers is more important.
Yes, that's the other way around. That do I want this to be in contact with me? And then do I really, it's from my point of view. Right now I'm talking about tweezers' point of view. Do I want to put it on just bare surface? I don't know what else has gone before on that surface, right? Want to put it in my pocket? I don't know what all I've been putting it there. So always use containers to store them. You always use containers. Use a test tube. Clean the test tube before you start doing your process. You need to have those squarish containers. So always after you process, it goes into a container, a closed environment. So clean room is clean, but we have many more further microenvironments inside the clean room, which are further clean, which are cleaner than the environment itself of the clean room. So anything that comes into contact contact to a wafer, you have to think about it. Where has that thing been? So if you don't know, clean that tweezers, clean that container. So there are many types of things we use to handle vapors. Tweezers are one. Then we have something like a handle where we have, so this guy is something, they have grooves here. So what we do is we put a wafer here and we push this down. So this also have groove. So now this guy is something which we can use to hold and dip into a solution. The whole wafer would dip, right? So this comes here, and so we are holding wafer from 3 corners. That holder needs to be clean, right? Because the back side is, so of course front side would be the shiny side, but back side is coming in contact with this holder itself, right? The edges are coming in contact here. So the holder needs to be clean. How do we clean? So we'll see what are the requirements of cleaning. Just like we do dishes where we put some soap, then we rinse it with running water, we call it clean. That's clean enough for food. For these, there are certain steps we have to do with certain chemicals for them to be clean. For air, there is always air circulating in clean rooms. So there are HEPA filters. What does HEPA stand for? High efficiency particulate something. So we'll see what are HEPA filters are. And air is, the airflow is always, what we call turbulent and laminar flow. You guys have ever heard of turbulent flow and laminar flow? Mechanical engineer, right? So what is turbulent flow? So if you break down the fluid flow into the lines of particles, they don't have any order, they are random, right? So that's turbulent flows. But laminar flow is when everything flows in straight line, right? So flow is much more aligned. We always want to have laminar flow inside the clean room. So the whole air is always being pushed up, pass through HEPA filters and coming through the floor again. This is general environment, and then we have these sort of wash basins, you can call them, but places where we do chemical processing. These are called hoods. So hood has further an isolated flow within that thing. Hood is nothing but a window. You open the window and there is this working room inside that, and we stand there and we do everything inside that hood. So the flow of hood is that local air is moving up. So whatever chemical I use, the fumes are not coming to me. They are going within that localized airflow. So we maintain laminar flow within the hoods also. What do you think? The airflow of hood will be mixed with the common airflow of the clean room? It's not. That is because it has many more vapors of chemicals. So that's treated separately and sent out. Right? So, and then of course, we have handling. Of course, these are the handling things, tweezers and all those which can bring in chemicals. So we give 100,000 to 1 million particles per minute. That's human. And city air has 5 million particles per cubic feet. These are common words. So if somebody says shoe cover, booty, gloves, coverall, face mask, hood, cap, safety glasses, you should know what is that, right? And of course, you all will be given one to get into the clean room. What can films do? So, you guys moved out of apartments and cleaned the grease from the cooking range. It takes an effort, right? Some of you have been here less than a year, haven't changed an apartment yet, but when you clean the cooking range, the stove, is grease, right? Have to use certain chemicals to remove it, but some are hard to remove. Same way, The reactions that we do, some of those reactions result into films. When they get deposited, it's very hard to remove them. We'll get some tissue from
Contamination. Thank you.
you're contaminating the classroom.
I have.
Coke is addictive or not?
Not corrosive.
So those films can ultimately result into degrading the cleaning process. So if you want to use run-of-the-mill standard cleaning process, they might not be effective. So you want to do aggressive cleaning process, they might affect the features that we have on the wafer. So they become an issue in cleaning. And if I have silicon and I want to apply photoresist, and we discussed about photoresist, we spin it or all that. So we know what photoresist will stick well to silicon substrate, right? But if there is a film in there which has, I don't know what in there, it won't stick well. So that's a very simple example, but there are many more things, examples that we'll see once we get along. And some of the things can chemically change on the substrate. So that's on the films. Elements can diffuse in the silicon and degrade device properties. Again, transistor, remember always transistor, we need to have control over the gate. If I can't switch it on and off, it means I'm losing control over the gate. And this can happen. So if I do this and flip it and nothing happens, it means I don't need it. It's not giving me any control over the whatever connection is going to make. So same in transistor, if I cannot switch the gate on and off to make the device conduct, I am losing gating effect. That can happen with trace elements. Particles, again, when I do masking, it's a physical transfer of design pattern. If my resist has incorporated something physically there, it will not result into accurate transfer of the image. So think about it. If on a surface I had this, I wanted to make a square from a mask by shining light, right? So if I had a speck somewhere here, a particle, and I did my lithography, I will get something like that, because this will stay there, right? So my image transfer would be not exactly what I had here. So if I had a square here which I wanted to transfer, and which can ultimately result into defects into the films that we deposit or lines that we make. So it can degrade the features that we make. And we defined the size of particles to be killers. They are how much? 20 to 50% of minimum feature. Now there are few new terms here. What is minimum feature size? As a designer, I make all sorts of components, resistors, capacitors, right? Channel length, source and drain. There is always something that is smallest in feature size, which I want to be transferred faithfully from mask to wafer. So that is the smallest feature size, and that will define what technology I will use, so what node I will use, so to speak. Like we discussed, there was 65 nanometer node, and so that minimum feature size will define what particle size can be allowed in that room. So even if we call it clean room, it always has some of it, but we get rid of most of those above certain size, and that defines a term called class. Class 1000 clean room, class 100 clean room, class 10 clean room, right? So what does a class tell us about a clean room?
How many particles there are?
How many particles are in there, right? right? Not exactly. How many particles of what minimum size would be in there, right? So it's not just how many we can clean, it's that what size we want to really get rid of. How do we get rid of different size materials? What's that process called? Filtering, right? So we have filters. What is a filter? How do we define a filter?
That removes something unexpected, what you don't
And remove something. So it's a barrier which has size exclusion. A membrane which has certain holes of sizes. So above that hole size will stay on the membrane, or the filter, everything else can pass through. So we can exclude certain size, above certain size. So that's what we want to do in a clean room. So the smaller the feature, the smaller is the requirement. The higher is the requirement, and more difficult it is to maintain. So because those filters will be special, they have to be maintained, because after a certain time filters get clogged. We have to measure if filters are doing what they're supposed to do. And so it makes it more stringent as we go down in that. So with the technology being pushed, having many more devices, much more dense device design, we are increasing the number of devices from 4K to 16 megabyte and all the way down. Our feature sizes are going down, and so are our killing defect size going down. Right? So we have to make sure particles above this size are filtered. So this is an example, not a very inspiring example, but an example of something that we can all relate. This is more of a laminar flow, and then it becomes a turbulent flow, right? For some distance, the smoke stays laminar, moving in one column, one line, and then it becomes turbulent. So we have these HEPA filters, high efficiency particulate attenuation filters. They get rid of particles of certain sizes, above certain size. Then we want to measure from the air, we want to measure temperature, humidity, chemicals. If there is a leak in a system, in some tubing, that chemical will end up in that air of the room. We may not be able to smell some gases or feel some of that, but we have sensors who would look for those. So that air is not just filtered, it is sampled also for all these things.
So if we're actually smelling chemicals in the clean room, does that mean the clean room is not as clean as we think it is, or is it that the smell is, the particles that we smell are too small to matter for our devices?
Hold on. Do we smell things in clean room? That's what you're saying?
No, what I'm saying is if the clean room is filtered, n times per minute, however many that is, we shouldn't be smelling any of the chemicals, right? Or is that not
the filtration is for particles.
I see.
Not for chemicals. Right. Can you filter chemicals out of air?
You can, probably not easily.
You can absorb them, but filtering.
I see.
Right. We put baking soda in our refrigerators. What does that do?
I don't know. I've always wondered that.
It sucks. It absorbs those odors. Odors are chemicals. It absorbs those. Yeah. Yes, don't know. We put baking soda. Just open the container and put it in the freezer and main refrigerator. It sucks all the odors from stuff that we put in. But we look for things that we don't want in the environment of the clean room. Why temperature is important? Unwanted reaction, okay. But we do many wanted reactions in there. What does temperature do in reactions?
controls the rate?
Changes the rate, right? So all of the processes that we do, we are doing reactions essentially. We want to control the rate. We want to know exactly how fast, how slow it will go, right? So only then we can set up the parameters for the reaction and expect certain results at the end. What does humidity have to do? Photoresist essentially is a very, very fundamental process that we do. Photolithography, in which we apply photoresist on the wafer. That stickiness of resist, or its exposure, or its development is highly impacted by humidity. So lithography, you'll see, I've seen it many times. Students would say, "Oh, I did lithography like 5 times and nothing worked." And I said, what was the humidity in the room? So every photoresist, every process has a humidity range that it will behave in that. If we are above or below, it's not good. It's not going to work. So many times we shut down clean rooms if humidity goes way up or down. Happens a lot in Texas. We are seeing that, right? So within one day it can fluctuate heavily. And it depends on, so there are certain things which we can control, certain things which are, if you want to control them, you need specialized equipment, which we may not have. So humidity, I've seen many clean rooms cannot control humidity very effectively if the outside humidity changes too much. So we look at those, we see for vibration in clean room, we see for electrostatic buildup. Why would be vibration important to monitor in a clean room?
Exposure?
4,000 RPM. Where do we do 4,000 RPM? We rotate things at high speeds. Spinning for photoresist application, right? I gave you that example. So you don't need vibrations here, right? What happens if you are spinning something at such high RPM and you have vibration?
It will become unstable.
Good.
Stability will be lost.
Stability. So you have this moment of inertia, right? So if you have an unbalanced axis, what's going to happen? There are going to be unbalanced forces on the wafer, and whatever vacuum you apply, your wafer is going to fly away. And here goes your 1 year of your hard work on that, devices you have been making, right? So we want to control vibration. More importantly, when we do microscopy, especially electron microscopy, which are huge machines, and we are magnifying at, 80,000 times. So we are really going down on magnification. If there is vibration in the platform, in the floor, it was very hard to focus your microscope, electron microscope, right? So we need to control vibration. Charge buildup, again, when you are doing your processes, wafer has to have controlled charge. We do bias our wafers during many processes because we want the reaction to happen fast enough. So we do bias them. If we have a positive one that we want to react on the surface, we may bias it to negative bias to the substrate. So we don't want uncontrolled charge buildup as well. So there are two types. One is benches where you have a whole floor, where you have equipment, and the auxiliaries, pumps, power supplies are at a different level. So that's called a ballroom type of clean room. Or we have something, what is the case here, we have two different sort of walkways. So one is which is part of the clean room, and you have front end of all the equipment. Then the next one is within a door, it's not clean enough, it contains all the auxiliaries, pumps, power supplies, cylinders. So it's on the same floor. So that is, one is called bay, where we work. The other one, the servicing place, is called the chase. We seldom go into chase. We will never go into chase. If there is a problem, we tell the equipment manager, they will go into the chase. We work in the base. right? So there are two types of it. So this is something which is again showing the air is coming very, oh, I did say opposite before. So air is coming from the top, being sucked through the bottom, and serviced again through filters and coming back in there. Right? So this is an example of a bay and chase in questions. You guys will be seeing that very soon. So your guys will be getting into the clean room. So maybe some of it will seem strange, but we'll be spending lots of time in there. I want you to know this thing.
Do we need to get our own tweezers or anything?
You'll be given everything.
We don't need to.
Yeah, what you were supposed to bring yourself, I've told you, will get you everything else.
How about goggles?
We'll have goggles.
Oh, nice.
Yeah. Right? So this is ballroom and bay chase where you have the cabinets, controls, all in one part, and then next one is where you go what you got front end of those equipment, all the machines, and same it repeats. Right? So this is where you have microscope, everything, and the chase is what you have, all the auxiliaries for that equipment. So, as I said before, within clean room we have then further smaller, cleaner environments. Right? Your tweezer goes into a case. Can be a test tube. You guys have seen test tubes, right? Test tubes in high school chemistry. So, if you put a cap on the test tube, you can use that to store a tweezer. I always used to do that when a while I had a tweezer. But that is, so of course you clean your test tube before you start doing that. So that is it, and then you put a cap on it. Now you can put that tube anywhere. Your tweezer is not coming in contact. Similarly for wafers, we put them always in a container. We never leave a wafer unattended unless it's in a box, closed tightly. We don't move wafer by holding it in an open environment from one place to the other. We always put it in a container, close the container, and we move the container. For industry, they don't work on one wafer at a time. They have cassettes, big cassettes, which have multiple wafers in there. And the whole cassette is moved from one place to the other. And every module has this receptacle where it captures the cassette and then takes one wafer out at a time, or whatever the case may be. So these are called SMIF, Standard Mechanical Interface, where you have this box and wafers inside. What we will use here, something like this, or a single wafer carrier. For your case, it will be a single wafer carrier. It will have a base and a top, right? So the top will be screwed in. It's screwed in opposite to standards. So it's screwed in like this, screwed off like this. We are used to screwing in things like this and screwing off like this. So we always place wafer in there, close the cover before we take it to the other place. Sometimes you may have something called a spider. So spider is again a plastic thing. It's made of what do you call it? Teflon. It's a plasticky material. We'll talk about Teflon. So what it does is it's a spring type of thing. You put it there, and once you close it, pushes the wafer down. So wafer has no play within the carrier. So from open boards and cassettes, they have moved in industry to what you call the pods, or this boxes, mechanical boxes which hold them in. Each machine can interface with them and get those wafers out of them for whatever processing and put them back in there. So this is what we call mini environment or micro environment for the substrates of the wafers. So this is on the clean room. So it's particle size and the total particles per meter cube. That is what defines class 1, class 10, class 100, class 10,000. So it's not just how many particles? It's the size of particles. So if we push down to the smaller particles, we are a little bit relaxed on how many particles can be allowed, right? So what class do we have here? What's the class of our clean room?
10,100, right?
1,000? 100?
100,000.
100,000? 100,000? That's 100 and 1,000. Some parts are 100, some parts are 1,000. What is teaching path? I think it's 1,000.
It's 10,000.
Right? So what does class 1,000 would mean? Look at the plot. A class 1,000 would mean, look down and see, starts from here, goes down. So bigger particles are way smaller in their quantity. Make sense? These plots make sense? So bigger particles are much less in number, right? So and then we go all the way to what size? 0.1 micron? How much is 0.1 micron? 100 nanometer, right? How many do we allow? 10 raised to power? Wow. A little close to 100, a million, right? It's as the size goes small, it becomes hard to filter that. In class, maintaining that integrity is not always only the filtering, it's users' behavior also. It's not always just how good the equipment works, it's how good the users are. You'll see people doing stuff that you would want to pull your hair off, and they'll be qualified and they'll be publishing papers, but you see their behavior in the clean room, they don't use common sense. So people are major contributor to degrading the class, right? You won't be able to comprehend what I'm saying, but you'll see things that you do, people. There is a pass-through in the clean room. You guys seen that? You must have been told about that during training. What is pass-through?
Is it where the air is blowing?
It's
The
a
little.
it's a small window in the wall. So it's used to, if you want to move something in or out, you don't hold it and you step out. You open, so it has two doors, one in the clean room, the other one to the outside. Those two doors cannot be opened at the same time, right? You see, so what you do is you place stuff in there from one side, you close this one, once you get inside, you open the other side and you take it out. You don't leave your stuff in there, right? Because that can contaminate other people's stuff, whatever they're moving. You'll see many things there. Sometimes they're open for both sides. We maintain positive pressure inside the clean room. What does that mean?
More pressure than the environment.
So inside is pressurized. So we can always, why do we pressurize clean room?
So that dust from the outside doesn't blow
So
in.
outside air doesn't come in. So even if there is a opening somewhere, air is always moving from in to out, then out to in, right? So it may feel strange to some of them if they have sensitive to pressure, but get used to it sometimes. So this is an example of what I was saying, the hood, chemical hood, where we work on chemicals doing process on our wafers. Common sense. So when you look at the hood, there are grooves, there are holes maybe on the side of the working area. But of course, you want that continuous working space to put your beakers, your chemicals, your bottles, your whatever. You'll see some people would leave their Kim wipes. Kim wipe is sort of like we have napkins or wipes. So these are special wipes which are used inside the clean room. They don't have loose,
particles?
What is like this thing that
Fibers?
Fiber. They don't have loose fiber. So you use special kind of wipes in there. Because if fibers come off, there are also contamination there, right? So should we leave something to restrict those holes? That's gonna, if you do that, I'm basically breaking the laminar flow inside the hood. If I do that, the vapors are gonna come to me because I'm not letting the airflow in a continuous flow. So you see those things, and you have to be careful. You have to use common sense that should this be done or not. Then on the hood, they have these markers, maybe by the manufacturer, maybe written by the staff, where they'll put an arrow and they'll say the hood should not be opened above this. The hood is a window which can go up, down like this, and it has these glass doors which can be slide to side. So it says you should not move it above this. You should not move it above this, because if you do that, then the flow is, the air is coming out of the hood as well, and you don't want that. So those are mini environments that we want to maintain, where within the hood we want to maintain the flow of air. You guys have seen this rule, AAA, right? AAA. Always add acid. What does that mean?
Never add water to acid.
If there's acid supposed to go into some solution, we always add acid. We never add something to acid. Make sense? We never add something to acid. Discuss that if you do that, then you have the whole acid mass to start reaction. It blows up. So we add acid, so the reaction continuously takes whatever speed it has to achieve. So how do we clean things? So we all agree we need to clean.
Yeah.
We have to stay clean. I don't mean that, but we are thinking we have to keep the gowns and our receptacles, whatever we use, clean for reasons that we have discussed. How do we clean all those things? Okay, why do we want to clean? So a quarter of steps in a fabrication run are just cleaning. So we take the substrates out of the one process, we clean. So many times we have to clean, which is necessity. We might have done some reaction with an alkaline solution and we want to neutralize it. What are alkaline solutions?
pH greater than 7.
pH greater than 7? Basic solution, right? KOH has potassium hydroxide. Potassium is considered a metal. Can degrade device if it seeps within the substrate. So before I do any high temperature process, I want to neutralize any potassium if it is there on the substrate. Right? So cleaning is not just always cleaning, you have to neutralize some chemicals that might have come in contact with the substrate. So can be carbon left over from polymer from some reactions which happened before. Can be particles, can be films, can be oil. So we need to we clean after almost every major process. And water is one very important agent that we do for cleaning. But water itself is not clean as such. We have to clean it. We have to deionize it. What are things in water? What are the things in water that can be problem for processing? Of course, ions, Deionize, it means you want to get rid of ions. What else can be there in water? Salts? Yeah, deionization, salts become
You
ionized.
can have particles,
Particles?
organic particles.
Organic particles? What else? When you say clean drinking water, are we talking about particles? We're talking about living things in water. Minerals is again salts. Or,
Huh?
so we're talking about
Bacteria, protozoa.
so living things in
Fungi.
water, right? Want to get rid of all these things: ions, salts, minerals, particles, living things.
We got organic chemicals too now.
Organics, very important organics, because what is an organic material? That contains carbon, and we say carbon everywhere. Carbon can make a film which is becomes hard to remove. So we want to get rid of organic materials. We do on-site DI treatment. So these DI water systems can be as small as a bench top to something that fills up a room. Depends on throughput and the quality that we want. The throughput is probably more important. Many times in literature, you'll see water to be written as 18 megaohm centimeter water was used. So it's a measure of removing ions, right? Because pure water is, what do you think? Pure water is conductive or not?
Not, well,
Pure water is not conductive.
at 18 megohms per centimeter conductive, so it's very resistant.
So pure water is not conductive. What causes the conductivity through water? Sodium? Sodium?
Chloride.
Chloride. Salts, right? So salts, anything that can ionize into. So we want to get rid of that because we don't want those salts to be there. There are many reasons why we don't need salt. First is, of course, if you have salts, they're going to contribute alkaline ions and they can degrade devices, right? What happens when you dry water solution, sodium chloride water solution? What happens? What is left behind?
Residue.
Crystals, residues, films, right? They become particles. You don't want that. So there are multiple reasons why do you want to clean DI water. High resistivity. All organic and inorganic suspended solid particles, microorganisms should be removed. There are gases in there you want to remove. Oxygen, silica, metals. What we call TOC, total organic concentration. And there are specific numbers that it has to be below that number. So whole lot of processing has to be done on the water. Want less than 10 parts per billion of TOC. And where they come from? Naturally occurring microorganisms, organic matter, man-made organic based chemicals. All sorts of things are there in tap water, which is good for drinking, not good for processing.
Why 2,000 gallons per wafer? I mean, we're not going to use that much water in there, are
We'll
we?
see how much you're going to do that. Yeah. At the end of every cleaning process, there is something called DI water rinse. DI water rinse is where you hold the wafer and you put it in flowing water. You rinse it. So the book says mostly 5 minutes rinse. So it means your tap is running for 5 minutes and just for one wafer. In industry, of course, they have the cassettes where you are flowing water to remove whatever is there.
Does it take more than a gallon of water to make a gallon of DI water?
I have no idea. Look at the specs of DI water system. They should have this information. So what we want is to remove particles, remove bacteria. How do we kill bacteria? How can we live? How can we kill living things in water? Heat it, right? But there are organisms that live in hot springs also. we know those all over the world. They have these springs which are hot water, sulfur. They have living things in those water as well.
Some chemicals.
Pardon?
Using some chemicals.
Chemicals. Right, then we'll have to remove chemicals.
UV, I think your best bet is to filter, right?
UV. Filters, yes, you will remove things, but there can be living things smaller than 200 nanometer, which is.
I mean, do we really care if they're living or not? Because if even a dead bacterium is still going to contaminate your device.
Right, so I want to filter it, of course, but I want to kill it also.
I see.
So those, they don't pass through filter and result into colonies. They can still
I see.
create colonies. So I want to kill that. UV is the easiest way to kill living things, right? That's why we have these glasses with protect UV and sunscreen which protects UV, because UV results in the mutation of DNA, ultimately kills the thing. So UV is something that we pass the water through, and then we filter. So what it does is it changes the organic matter. Living things have lots of organic stuff. Results into carbon dioxide and water. So bacteria, what we aim at is less than 1 CFU per ml. For bacteria, the unit is CFU per ml. Colony forming units per ml. So if they are not killed, just filtered, some of them would pass through, they'll start forming their own colonies. So bacteria are counted as CFU per ml. So we want to do that to destruct ozone as well. What is ozone?
O3.
O3. What is good about ozone or bad about it? What is good about ozone? Absorbs UV, right? What happens when it absorbs UV? Breaks down into simpler units, oxygen. But it's highly unstable, which means it reacts easily. It corrodes the piping. If it corrodes the piping, we can use it to clean the piping as well, because something that corrodes, it means it's going to take away material from the surface of that pipe. We want to control how much we clean. We don't want to eat away the pipes. So we want to remove ozone, but we want to use it as a system sanitizer also, controlled amount of ozone. So that's also something that's coming with water. Okay. And then this is water. So every step requires, every cleaning step would, most of the cleaning step would require water rinse at the end. Many times it's not, the first thing is not just to clean it, first thing is to neutralize the reaction that is going on. If I dip a silicon wafer, silicon dioxide, a wafer which has silicon dioxide, I dip it in, what do we use to etch silicon dioxide? I didn't want to give that right now, but I'll do it. So it's very important, always remember that. You'll see a lot of it. BHF, buffered hydrofluoric acid. It's also called buffered oxide etch. So it's used from 1 to, I think, 6 to 1 to 10 ratio of DI water to acid. So we dilute acid. Of course, when you dilute, 6 times would be water in there. So say if I dip my wafer, oxidized wafer into BHF, and I've timed it, so in 1 minute I'm done with how much etching I want to do, I take it out. How do I stop the reaction right here? Because some of BHF is going to be on the wafer. What do?
Rinse.
Put it in water, in beaker full with DI water. Rinsing will still not be consistent right away. But a beaker full of DI water, if I dip it in, it's going to dilute BHF right away. Right? So I can pretty much control the reaction, stop right away. So that's also, and you'll read another typical word, conspicuous amount of DI water, which means something which is a lot of DI water that can neutralize the reaction. So it's just one example. Many reactions that we do in liquid, first thing is to take it out and put it into a beaker with DI water, so we can stop the reaction, at least retard it to a great extent. So that is for the DI water. We want to do it for rinsing, to stopping reaction. Where else do we get contamination from? During processes, we do deposition. The deposition is done where you might be physically depositing something or reacting some compounds on the surface, which result into material that gets deposited. So it might have some byproducts, which we do all our efforts to suck out from that chamber, but some of that can get back on the substrate, get back on the liquid. Some of that can stick to the walls. We will be going through this over and over. When we go in chemical vapor deposition, we'll look at this again. So if you feel that it's too much knowledge and it's new, yes, but we'll see it at many places. So don't feel overwhelmed with this. So many processing, almost all processes will result into byproducts, whether it's chemical vapor deposition, CVD, whether it's etching, where we pump in certain gases which etch away certain materials, and they may cause flaking of the. So if this is a chamber and I'm placing my wafer there and I'm pumping my gas from here or maybe here, and I'm sucking from one of these openings the products that come out, there will be still some that will, the reaction which will flake the sidewall, sputter material, remove some material which can deposit it on the sidewalls of the chamber or on the wafer itself. And it can result into some byproducts which are polymeric, which are long chain molecules. It can come from the handling of the wafer, from tweezers. It can come from the gas O-rings or parts that move. So many places that we can get contamination from within a process. So they can not just deposit, they can create charges also. They can create electrostatic charging of the surfaces as well. And if you don't clean the chamber, and cleaning is not always a manual process where you have to wash the dishes. You can just put the dishes in the dishwasher and turn the button on. So there are processes which are clean processes. So especially remember that oxygen is always a very strong cleaner. Wherever there is oxygen involved in a process, it's a vigorous process. So to clean a chamber, we do a process called oxygen de-scum. Scum is formation of different materials. De-scum is removing that material. Oxygen de-scum is a cleaning process. We do that very often. Many times I would always do a de-scum before I do my process. And to be nice with the next user, I will do it at the end of the process. We don't do de-scum with a wafer inside. We do it on an empty chamber. Right? So
What kind of devices do we do this in?
What kind of?
What kind of devices do we do this oxygen de-scum in? Is it?
Oh, empty chamber. We just want to clean the chamber. So it is done on plasma. Any plasma system will have a de-scum recipe. Recipe means the combination of gas flow, temperature, how much power we have to provide. So before I do the actual process, I will just run that de-scum process, which will make sure the inner walls of the chamber are cleaned up. And then I will open and place my wafer, and then I will do recipe of whatever I was supposed to do. So we do this a lot of time to reduce cross contamination. something that was happened before shouldn't affect what I'm doing. All right. How do we clean wafers? How do we clean, say, let's start with tweezer. How would we clean tweezer? Get a new tweezer. What should I do to get rid of anything? We start with something called solvent clean. Now, solvent is simply stated something can dissolve other things, right? So, solvent in this case we consider as non-acidic, non-basic solutions. What are those solutions which are not acids, not base? Acetone, alcohol. So acetone is a very good cleaner, very good solvent. What we do is we dip maybe one wafer and tweezers in a beaker filled with acetone. Leave it there for 10 minutes. Leave it there for 10 minutes. It's going to remove everything. The nail polish remover has very small concentration of acetone. That's why it can be used. But acetone is not a good solution. We don't want to inhale it. So, but first step is we put it in a beaker inside the solvent hood. Leave it there for 10 minutes. Now, once I take it out, it's going to dry off. Acetone dries off very quickly. It will have residues of acetone in it. Now, how do I do it? What do I do with that? I dip it in methanol. Methanol is going to dissolve acetone, right? So acetone, I used it to dissolve any organic material, and methanol I use to remove acetone. After methanol, I can just rinse it with clean water. And that's a process called solvent clean. Before I go into these much more involved processes, solvent clean is a simple process which gets rid of many basic organic materials. I can use solvent clean on wafers as well. It's a comparatively very delicate, should say delicate, but relatively it's less harsh of cleaning. And when I use acids in any type of cleaning, those are harsh treatments. So if I have devices which are very small, which features, maybe I have some metal deposited which is 10 nanometers wide, I want to stay with solvent clean. I don't want to do acid treatment there. So it will depend on your judgment, what kind of cleaning you want to do. So now, going back to the standards, what we're going to do is, how do we clean wafers? So every cleaning step would require your understanding of what is already there on the substrate. If there are many layers of devices that have been made, we may not be able to do certain cleaning steps because they can destroy those devices that has happened before. So those are then divided into what we call FEUL and BUL locations during the process. So front end is where we have nothing, we just have simple silicon or maybe silicon dioxide. We don't have too many layers made up yet, not too many metals deposited. It's called front end of line. We have much more room for what we can do. Right? We can use aggressive chemicals. But once we put metals and different layers on there, we have very small window what can be done. And we can only use less reactive or, so to speak, tender reactions to do that. So front end of line, a very popular one is called Piranha clean. Piranha is mixture of hydrogen peroxide and sulfuric acid. From your experience or knowledge, tell me what happens when you mix acid and bases in equal amounts. What do you expect?
They neutralize each other and
They neutralize each other? Okay, that's least of my worries.
they release heat.
They will?
There will be a lot of heat involved.
Lots of heat, explosion. They will blow unless I add acid in the reaction, right? So my question had a basic flaw that what happens when you add them? It's going to be big explosion, very, very exothermic reaction, unless I add acid to hydrogen peroxide, right? Now, what would, if I have 1-to-1 of both, or if I have 1-to-3, I have 3 times of hydrogen, sulfuric acid, which one is going to be more aggressive? 1-to-3 or 1-to-1? 1-to? Okay, let me say it again. If I have 1-to-3 and 3 times is sulfuric acid, H2O2 to H2SO4, 1-to-3. Say if I have, it says 7-to-3 here. I'm saying 1-to-3. So if I have 1-to-3 and 1-to-1, which one is going to be more aggressive?
Probably the 1-to-3.
This one or this one?
I guess 1-to-3.
1-to-3. A lot more acid is reacting there, right? So, of course, it's going to neutralize essentially when the whole hydrogen peroxide is used up, but you have much more sulfuric acid to do that reaction. So you have many more of sulfuric acid that doesn't react, but you have the whole reaction is very aggressive, much more aggressive. So we use, okay, standard is what book says 7-to-3. We use 1-to-1, we use 1-to-2, 1-to-3, many different ratios of. So if you use, okay, yeah, now I see what you're saying. I was thinking the other way around. I was thinking first hydrogen peroxide and then sulfuric acid. So yes. So here it's almost double. 3-to-6 would be 1-to-2, so it's 7-to-3. Sorry about flipping the order here. And it gives highly exothermic, very hot reaction. During that reaction, what it does to the wafer is it etches away whatever is there on the surface, right? Okay, so there was supposed to be an explosion if you add them. What else would happen if you add 2 acids and base together? Again, be lots of heat generated, lots of bubbles that will come out, right? There'll be a gas formation in that process, right? So that bubbling results into cavitation. It etches materials. So we use that many times for simple cleaning, gets rid of almost everything. RCA was a company, electronics company, equivalent to maybe Toshiba, JVC in USA. So RCA was an electronics company. So they developed this process. They are called RCA clean processes. RCA's name doesn't mean anything about the chemicals or whatever, but it was developed by that company. Then there is called standard clean, where we have water, again a base, and hydrogen peroxide. It gets rid of organic films, metals, and particles. To remove oxide, we use, I said that before, BHF. It's also called BOE, buffered oxide etch. Remember always, whenever I say oxide is going to be removed, simple thing is BHF. We always do BHF. Its etch rate is 1000 angstroms per minute. Normally. So. How many nanometers in 1 angstrom?
0.1.
0.1. Start playing with these angstrom to nanometer to micron, right? 10 raised to minus 6 micron, 10 raised to minus 9 nano, 10 raised to minus 10 is angstrom. So we use this angstrom and nanometer alternatively. Be comfortable. And then there's what we call standard clean 2. Again, now this one has acid, hydrochloric acid in there. it gets rid of atomic and ionic containment. In all cases, what we do is DI rinse and dry. And we store them in nitrogen. Why nitrogen? Why do we choose nitrogen ambient? Nitrogen is global. Nitrogen doesn't react at room temperature. So we do nitrogen for that. There are different ways how do we do rinse. We'll talk about that next time. Generally, the simple is water rinse. You open it and then there's something called cascade where you have a sort of a river of 3 compartments where DI water is, first one is filled with DI water, overflows into the lower one, overflows into the third one, which is lowest in height, right? So we start with, tell me something, should I start with the top one or should I start with the lower one? Just lower one, top one. Top one? Okay, if I start with the top one, it has got some chemical out of my wafer that is flowing to the next one. So which one should I start rinsing? The top one or the lowest one? Cascade is nothing but a container which has 3 pockets. We fill the top one with DI water, the water overflows, comes to the next one, that overflows will go to the next one. And there's a continuous flow of water. So when I have my wafer, I need to rinse it. Should I start with the lowest one?
I'd start with the lowest one and then go to the.
Then go to the upper ones.
Because you're trying to successively make it
successively
cleaner, right?
clean the wafer in cleaner DI water. Right? We'll talk about it.